Hello YouTube. Today I am showing just how you can quickly throw together a way to test exotic tubes or even non-exotic tubes like audio tubes, 6L6s, EL84s, etc. In this specific case, I have a 8068. I actually have two of them, if we can get it into focus here. They came from a Fluke 412B power supply. They use these tubes as series pass regulators for a high voltage precision power supply. These tubes are pretty unique. They can actually handle 3,500 volts across them. Now they have a little bit of a lower current rating, but they are able to handle this large voltage due to the fact that they're mostly designed for circuit regulation. So what I have set up here is a high voltage power supply. This is an electrophoresis power supply. You can get them pretty cheap on eBay. This one was 120 bucks. It's programmable voltage, current, or power limiting. It has some nice measurement readouts as well as a DB15 interface. So for projects that you want to remotely control it, you can do that as well. The only downside to this type of a scope is it does measure leakage on both terminals. So as much as I wanted to measure transconductance on this tube with my scope and a signal generator, as soon as I put the scope ground into the circuit, it trips out the supply. So because of that, the way I'm going to test this tube is just running it at a nominal datasheet configuration. So let's take a look at what that setup looks like here. Alright, looking at the basic circuit that we're trying to set up here. We have our tube, and we expect a nominal 0.9 amps for the heater. One thing worth noting on these series regulator tubes is their voltage screen max is actually really low. It's only 250 volts in this case, and then the plate max is 3,500. It has a maximum plate power output of approximately 32 watts if I recall, so you can run quite a lot of power through these systems. So the datasheet, one of the two recommendations, and this is close to what the Fluke power supply runs, is a 600 volt plate with a negative 7.5 volt grid and a 125 volt screen. Should produce a plate current of 36 milliamps. And that'll be dissipating about 22 watts on the plate, which is a good indicator that if we can pull 22 watts, that tube is still in good condition. Now, looking at the circuit, what we have here is a 4.7 k ohm resistor, and running that approximately 36 milliamps ends up with about 600 volts on the plate. I could theoretically remove that resistor. It's just there for safety purposes, and originally when I set this up I wanted to be able to measure transconductance with a scope and signal generator. Here you see a combination of a static as well as a potentiometer to cathode bias the tube. Again, if you wanted to do like a curve trace really accurately, you'd want to use a fixed bias on the grid, but in this case I'm just doing a cathode bias again. If the tube fails or something, that gives some level of protection. And the screen voltage, I have a stack up of some resistors, a 250K pot, a Zener diode, and then a capacitor to help steady that voltage because it's pulling it off the plate of the tube, and I didn't want to cause any oscillations with that. Again, a fixed voltage off of your power supply would be better, but in this case, this is a good enough situation. And the grid is tied to ground with a 4.7 k ohm resistor. Plenty strong that it should remove any oscillations, etc. So let's see how it works when we turn it on here. So now that we saw what we're going to do and kind of how this circuit is all set up here with the 4.7K, the screen potentiometer and the bias potentiometer, this meter over here is going to be giving us the grid voltage readout. This meter over here is going to be giving us the screen voltage readout. We'll just measure the primary plate current here. Technically it's the plate plus the screen, but the screen has a lot of resistance in series with it and should be drawing less than a milliamp, so it's good enough for what we're trying to judge here. We'll start it up, this power supply. Nice current limiting feature there. It says 6.5 volts, but actually I measured it. The output under load is approximately 6.3, so that's exactly where we want to be. Give that a minute to start up before we kick in the high voltage. I already ran this earlier, so it should be dialed into approximately that 125 volt screen voltage and about negative 7.5 volts on the grid. We'll expect to see 36 milliamps, so let's turn it on here and see what we get. Alright, 127 minus 7.2 and 34 milliamps. So that is a pretty good indicator, the fact that we were able to reproduce what the datasheet lists, that this tube is operating appropriately and it's actually in pretty good shape. I would expect the transconductance, if we measure that, is spot on to the nominal 5200 micromohms as well. With that, thank you guys for listening. Hopefully you found this interesting,